Hello, how is your linear algebra? Are you good at multiplying matrices or at computing eigenvalues or at inverting a matrix? Yes? No? Well, you're saved because this paper solves 9 linear algebra problems with transformers. Wait, Miss Coffee Bean, why do we need transformers to do this? It's not like we wouldn't have exact programs computing these things. Well, thanks reviewer 2 for ruining the research mood by asking practical questions here and doubting the usefulness of a transformer solving linear algebra problems. And to you, our viewer, welcome to this AI coffee break, where we will explain how a transformer can do linear algebra and also why this is cool and a useful thing to do in the first place. But do you know what else is useful? Miss Coffee Bean that brought a sponsor for today's video. Thanks to Weights and Biases for supporting us for this video. Now we can fill up our coffee machine and the chocolate box. And do not tell us you were living under a pile of coffee beans and did not hear about Weights and Biases yet. Weights and Biases is a MLOps platform helping you to build better machine learning models faster. It helps you track your experiments with beautiful plots. Did it ever happen to you that you overwrote training settings for a special model and you couldn't reproduce it anymore? Well, with Weights and Biases, this will never happen again because all the configs are saved. And you can use sweeps to optimize hyperparameters while sitting back and drinking your coffee. Well, surely this luxury is super hard to integrate. Wait, what, it isn't? You can integrate Weights and Biases with just a few lines of code. Okay, then how much money do I have to spend for this luxury, Miss Coffee Bean? Nothing, because it's free for personal use and for academic teams. Alright. Of course, if you're one of the big players, you have to take out some money off your thick wallet. But if you're a student like me who wants to stay organized even in the advent of the paper deadline, while all your coffee beans are going crazy and everything's a mess and irreproducible from that chaotic Excel spreadsheet you use for tracking experiments, then you should give Weights and Biases a try. Now let's get back to our linear algebra. In this paper, the authors say, we consider problems of linear algebra. We? Who now? We, Francois and Charton, right? Just kidding, we are laughing about a scientific way of writing we even when the paper was written by a single author. There are even better things to laugh about when it comes to scientific publishing, like for example the case of the physicist who used his cat as a co-author to conform to publication standards. Read that story on Wikipedia, it's linked in the description below. So they, the authors, use a transformer to perform 9 numerical calculations from linear algebra. Matrix transposition, matrix addition, matrix vector multiplications, eigenvalues and eigenvectors, singular values and SVD, and finally matrix inversion. But why would anyone ever want to do that? It's not like we do not have algorithms for these problems already. Why do matrix inversion with transformers? Well, we have at least one reason we could present to you. I think Miss Coffee Bean is not the only one who is curious to know. What are the limits of what transformers can do? Can transformers be applied on text? Oh yes, they can. Can they process images? Yes, they can. Do they work on speech? Of course they do. Can they do math? Well, it depends on what kind of math. We had a video where we explained the transformers that do symbolic integration. Transformers also have been shown to prove theorems, do formal logic, solve SAT problems, symbolic regression, dynamical systems, and so on. See the paper for references. So for symbolic mathematics, transformers seem to work well. But how are they with numbers? Luckily, this is what the authors are basically asking too. There have been investigations on sequence-to-sequence models for arithmetic tasks, showing how transformers do not work that well on this. Check out the related work if you're interested to know about this part. But the linear algebra problems, as chosen by the authors, answer a broader spectrum of questions, from little, easy tasks to complex ones. Can transformers do basic operations on individual coefficients of matrices, like it is the case with matrix transposition and addition? Can they also do compositions of several arithmetic operations, like it is the case with matrix multiplication? And then can they even do complex non-linear transformations? with cubic complexity, like the matrix decompositions and matrix inversion. And then what about generalization? Does a transformer trained on one type of matrices generalize to another type of matrices? And also, what about few-shot learning? Can trained transformers be further tuned to solve even larger problems by only a few examples? A few, this is few-shot learning after all. So you see, the test here is big, ranging from simple operations to more complicated arithmetic to advanced algorithms I learned about in university in my linear algebra classes, but Miss Coffee Bean to date has not heard of them yet, so she calls numpy.linalg all the time in her blissful programmer ignorance. But I see you are not convinced or motivated yet to use the transformer overkill to solve these problems. Are you reviewer 2 here? Then let's look beyond the paper into even more arguments made by the authors during their rebuttal. One argument is that it is important to test the limits of transformers if we want to apply these to science. Just think about DeepMind's AlphaFold in biology or transformers as a replacement for Mathematica. So the question is whether certain computational building blocks can be performed inside a transformer. Because if yes, then one step is clear when chasing the question of applicability of transformers in science. They can do linear algebra. One more argument that the authors make, which Miss Coffee Bean seems to like the most, is that transformers are usually used as end-to-end solutions. Let's suppose that for the solution we must compute some arithmetic operation or some linear algebra. It would be impractical when time and resources are critical to step out of the transformer to perform these operations. So having a network or a subnetwork implementing these operations in neurons is simply comfortable and practical. 2 more arguments focus on providing general insight on transformers that are small. We are not talking about GPT-3 sized models here, but about shallow, simple models that one scientist can train on his GPU at home. Also, the encodings, representations, and insight can be used for purposes other than linear algebra. But okay, Miss Coffee Bean, enough with the motivation. We got it. This is research. It has all the positive practical outcomes we just mentioned. It's fine to do something only because we can and because we can learn something from doing it. It is research. It does not have to land directly into the App Store to make money out of it. In any case, now that we are overmotivated with transformers solving linear algebra problems and we think that is cool, let's dive into explaining how this is done. Well, to work on matrices with transformers, one needs 2 things: matrices and transformers. Of course, the challenge here is to represent the matrices, so the input, into a format that a transformer can process. The other challenge is to understand transformers. For this, maybe you want to check out one of our previous videos. We remember that transformers work with sets, and if the set's elements have an order, we speak of sequential data. The transformer encodes the order of the data in positional embeddings, and matrices have a structure, an order, so we need to somehow transform these 2-dimensional tables into sequences. Nothing easier than this. One can do it by taking the numbers and writing them one after the other. Their order would be then captured in positional embeddings. The authors also prepend a coding of the size of the matrix. This gives the transformer further information about the matrix dimensionality, so the transformer can leverage this. But what have we done, Miss Coffee Bean? By just writing the numbers one after the other, we actually created a vocabulary for the transformer of infinite size, because there are infinitely many real numbers the last we checked. So encoding each matrix coefficient with just the number it represents is a poor decision, because the network would need to learn representations for each possible number in the infinitely sized vocabulary. With an infinite vocabulary size, it will surely happen that numbers occurring during testing will not have occurred during training. Then, is there a way to encode the numbers better and maybe have them represent some prior knowledge about numbers in general? Yes, there are at least 4 as presented by the authors. We are talking about P10, P1000, B1000, and Miss Coffee Bean, stop it with the cryptic codes. We are not talking about the Terminator. So what is meant is pretty clear from this table, that one can decompose a floating point number according to these rules and use a set of integer numbers, still infinite, but their infinity is smaller than the infinity of the real numbers, and other symbols. This means that the knowledge about numbers is explicated. For example, in the P10 and P1000 representations, we explicitly have the information of whether the number is positive or negative, and this is explicitly stated in a separate token. So yes, each number is tokenized into 5 tokens in the P10 representation, so the sequence length is blown up by 5 times, but this also means that the sign of the number is a special token in the vocabulary, so the plus token is shared among all positive numbers in the vocabulary. If we get a new yet unseen number during testing with the P10 representation, the transformer will have an easier time. The sign token is known. These integer tokens are also known. So there is a trade-off between how much a number is decomposed into a known vocabulary, making things easier, and the sequence length, making things also harder when training transformers. Cool, so now that we know how the authors encode their matrices into sequences, they just need to create training data. How? Is there a matrix database or benchmark lying around somewhere? No need, because one can generate random matrices oneself for the input. To generate the output, one just has to call numpy.linalg and get the solution. So say welcome to matrix solution pairs and gather your transformer and let them do their thing. As a note, the paper does work with relatively small matrices like 5 times 5, 6 times 4, 2 times 13. Of course, a next research question is postponed for the future about bigger matrices, thus longer sequences for the transformer and so on. In any case, training processes later, the authors come in to check onto their transformers and how well they did on each task. And well, surprise, 90+% accuracy across the board, at least with certain tolerance levels. Neural networks are probabilistic models, so one cannot expect exact results in each matrix coefficient. Yes, there are some differences between encodings where P1000 generally performs best, but the short lesson here is transformers do work on these 9 problems. Feel free to gaze at the numbers in the paper linked below. Because the real question about neural networks is, alright, but how does this generalize? This is AI researcher talk for asking whether the model is really understanding the task. But Miss Coffee Bean, why are you using the word understanding? That's off limits. Let's reformulate. So the question is whether the transformer has found the general algorithm behind, let's say, matrix transposition, so it can generalize to types of matrices it has not seen during training. That would be generalization. And this is what the authors investigate in 2 ways. The out-of-distribution generalization experiment. In a nutshell, the authors train their models with random n by n matrices that have the property that the coefficients are independent and identically distributed, sampled from a uniform distribution. Matrices fulfilling this property are known as Wigner matrices. Okay, so we have the Wigner matrices. How does a transformer trained on Wigner matrices perform on other types of matrices also present in science? Well, if the test set is composed of matrices with coefficients that just have a different standard deviation than the train set, the model only generalizes if the variance of the coefficients in the test set is lower than the training set variance. If one increases the variance, the probability to meet a number outside the training range increases too, and the model kind of fails because it cannot extrapolate. Miss Coffee Bean counts this as an A for generalization. We think Gary Marcus would say, told you so, neural networks do not extrapolate. Okay, then let's forget about the coefficient variance and let's look at the experiments where the eigenvalues of the matrices have different distributions. Well, again, if the distribution changes from train to test set, the results are again bad, if not catastrophic for some configurations. Then what to do in order to generalize? spoiler, carefully adjust the training data. What helps generalization is when, hold on to your chair, the training set is enlarged such that its distribution captures more of the different types of matrices. This goes exactly towards the point we made in our video about foundation models, that of course out of distribution generalization happens when we increase the training distribution so much that the whole world was in it. Yes, this paper is not enough to draw this conclusion, but hints into this direction. So no, we do not agree with the points made by the authors here that actual generalization happens. It might be very well that we mean something different with generalization, we think. But the point of the authors maybe is that by varying the training set, one can increase performance on out-of-domain tasks. But Miss Coffee Bean is allergic to these big words and argues that this is not the point of generalization, because generalization happens when the model got it and found the algorithm behind eigenvalue decomposition and can apply it successfully to really unseen distributions. But yes, it's too much to expect, sure, and if we are already at the generalization buzzword, let's go to the next buzzword. Few-shot. The argument of the authors here is that the models trained on small matrices, like 5 times 5, do not generalize to larger matrices. Then the model trained on 40 million examples can be further trained to also solve bigger matrices with about 25 million more examples. Okay, sounds fair. But what does not sound fair is that this is put into relation with the word few-shot. Is 25 million examples few-shot now? Is it just Miss Coffee Bean for whom few-shot is at most 20 or 100 examples? Since when is few-shot in the order of millions and more than half the amount of training data during initial training? What do you think? What is few in few-shot? And is this successful out-of-domain generalization as presented in the paper, or just wishful thinking but not quite? Or let's make generalization less of a binary variable. So we want to ask you, how much % generalization is there? Let us know what you think in the comments. Okay, Miss Coffee Bean, the terminology police Coffee Bean will go now. Do not take her too seriously on her rants about buzzwords. I'm writing papers myself and I must admit that buzzwords help. If these are loosely defined, evolving and changing overused words, why not use them to one's own advantage? Hey Miss Coffee Bean, you still here? Yes, you are, because you have something to tell. Look, we have been doing this Coffee Break quiz in our community tab for quite a while now. We have posted over 200 questions there already, and yes, we are kind of running out of ideas. So if you, dear audience member, want to contribute over there and you have an idea for a question, just email us and we will post it and we will also credit you.